Ladies and gentlemen, welcome to video number 29 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. We are today December the 18th in the year 2018, about a year later. Today we will go on in the discussion of the distribution of sunspots, spatial and numerical distribution of sunspots at the solar surface, and we will concentrate on the estimation of the numbers of sunspots per sunspot group. The contents of this video start with the introduction of the contents of the relevant section in the book, The Fivefold Sun. Then we'll go through observations and end with an interpretation of the found results. In the sixth part of The Fivefold Sun as a book, the third chapter of section 7 deals with the characteristic counts of magnetic bipoles spread among an estimated number of 10 sunspot groups on the solar disk. These are the sections in chapter 7.3 of the sixth part of the book The Fivefold Sun. We start in the first section with the observations, which will yield the estimated characteristic counts, and in the end of this video today we'll go through the interpretation of these findings. We start now with the methodology. The methodology is first of all to report from disk drawings from selected solar stations each of the counts read in the drawing where the observer on duty wrote in the number of spots for each of the sunspot groups that he or she drew. That's the basic principle. So we do not invent or re-estimate anything, but just report what was written for a count of spots per group by the observer on duty. From such disk drawings, we try to assemble a large data set, large enough to allow for the determination of two quantities. First of all, median values, which may include a decimal point. This is controversial as a definition for a median, not an integral value, but will be more precise. And secondly, the determination of modes even for very small sunspot groups which have few spots in them. So the data set sizes that we retain are at least 100 of days actually observed in each data subset, and in total we will have 1,235 observed days in our total database. In one subset, we intend to have a distinct solar cycle with its peak epoch. So we will have each of the last 4 peak epochs for these last 4 cycles. And we also want to have distinct sources. So we have 3 distinct sources: Cancelheux Observatory in Austria, the Royal Observatory of Belgium Uccle Solar Station, and the Sun array of solar stations of the US Air Force. So we now go through these data. Cancelheux, about 400 observed days with each more than 100 spots, plus the 150 observed days in just one rotation for 6 cycles, i.e. 6 times 25 days, which was shown in the previous video number 28. Uccle in Belgium, almost 300 days with at each more than 100 spots, and this is for the cycle peak epoch right after the epoch for which we have the data from Cancelhe. This is the 1980 peak, and this is the 1990 maximum of the solar cycle. And we have then the next peak of about the year 2000 from the Sun network. We have 300 observed days with each more than 100 spots. Finally, for the last maximum on record, about 2012, we have to have 2 stations at least to arrive at a significant number of observed days, 122 observed days with more than 100 spots each, because this was an anomalously low solar maximum and we do not have enough observed days from a single station. The results now for the median values for each sunspot group. These are the raw results, the first numbers, and these are the adjusted numbers for a total of exactly 120 sunspots, which, as we saw in video 28, is our best estimate, plus or minus 1 spot or two spots of the total number. In the next pages, we will show the results not yet adjusted, first for the 3 regular standard cycles, and then for the last one, which is anomalously low. So the observed median values are, you see, for the 3 different stations as follows here in this column: 46, 25, 17, 12. And we see that having more than 250 days on record in each case, observed days, we get more spots, especially for the large groups, compared to the numbers that we would get from considering only 150 days spread over 5 cycles for just one single peak rotations, as we can obtain from the Cancelhe archive. So here we get more spots, and the other difference compared with a single peak rotation is that for the very small groups we get more detailed. We get fractional values, e.g. 1.4 versus 2, which is very valuable. We refine our results by having so many observed days. The observed median now for the anomalously low last maximum epoch. Now we propose to adjust these found numbers, medians, for exactly 120 spots, and we get these numbers: 43, 23, 16, 11. What is interesting is in the bottom of the distribution, where we see that we have for the 11th group more than 1 spot in any case, but less than 2, so less than 1 bipole. Maybe we have only 10 groups that include at least 1 bipole, and the next groups have less than 1 spot, so they certainly are not statistically detected as physical groups. Now we turn to the mode of the distribution, and we will look for a raw mode, not adjusted for 120 spots for now. We will find from 963 observed days across 3 peak epochs that only the 9 largest groups have at least 2 spots in them. The 10th group, its mode is 0, and the 11th group, of course, as well. However, we also will find in the next page from this mode that there is a loss of about 20% in the number of spots when we consider the modes. So perhaps the 10th group actually has more than 0 spots. We shall see whether it is the median or the mode which is representative. So the mode values for the numbers of sunspots per group for 963 observed days, you see from the 3 different source stations, each for a distinct solar maximum, we find a value with most occurrences, which is here in this column, but we do not have these numbers for all groups. We can make an average of the 3 stations, and we can combine these two estimates in this last column. Here is the deficit, minus 12%, and the mode for the total compared to the median for the total. So you see we have in the bottom of the distribution the groups number 10, 11 and 12, which have for their mode 0 sunspots. If we compare now the median and the mode, we will find that the 10th group probably characteristically has at least 2 spots. The 11th group for its median again has less than 2 spots, and for its mode has less than 1 spot. So we propose that we have exactly 10 physical sunspot groups, the threshold being that the group includes at least 1 bipole, i.e. 2 spots. You see here this comparison. This is the median and this is the mode. We can, as a preliminary suggestion, try to approach a combination or an average of these 2 values and have the prerequisite that the number is a multiple of 2, so as to arrive at an integral number of bipoles. These are spots, and this is what we get, and a total of exactly 120 spots. However, here we would have a large discrepancy, retaining 2, when here we have more than 3 as a median, which is an important yardstick. So we propose finally to allow ourselves to split a figure which is not a multiple of 2. We will have to do the same for at least one other figure, and so we can approach better the size of the 8th group with 2.5 and the size of the 4th group with 11.5. It is interesting to note that if we compare with the sunspot area density threshold that can be found from some publications, we see that there is a threshold near 46 sunspots per group and a threshold near 24 or 26 sunspots per group. This is not shown here for lack of time, but we retain in the Fivefold Sun as a book the possibility that the true number of spots for the number 1 may be in fact 46 as well as 44. We translate the number of spots into the number of equivalent magnetic bipoles by an arbitrary division by 2, and these are the numbers of bipoles that we find for each group from the largest to the 10th largest, and you see that the 9th and the 10th have the same number of just 1 bipole. We go now into the interpretation of these findings. What is the type of distribution which is found, and if possible, can we assess why this would be so? We have to mention first descriptive statistical findings. The proportion of the spots in the largest group is about 37.5% of the total number of spots, so that the true proportion within the error bar, plus or minus 1%, might be 38.19%, which is defined by the mean and extreme ratio. If we now try over the entire distribution to fit a law, if we seek a best fit and try with a very simple rule, we first try with a factor 1.5, and we just see at the next page that it is not verified. So perhaps a factor slightly larger, perhaps the mean and extreme ratio may help. It will yield, if we try this special sequence of generalized Fibonacci numbers, which we have encountered many times throughout the Fivefold Sun project, the solar sequence. This is the first try with factor 1.5. We see that we predict a number of sunspots per group, which is in a strong excess in the top of the distribution, +6, more than +6 predicted B-poles. The total excess is similar, so that the entire excess is here in the top. This is not a good fit in this sense. And if we now try with 1.618, we find this sequence, 23 plus 14, etc., which is the solar sequence. Is it going to reduce the discrepancies? What is interesting is first to remark that these numbers are, as per part 1 of the Fivefold Sun, as a book. They are the numbers of differential rotation numbers over the Schwabe cycle. So if we decompose the Schwabe cycle in 1, 2, 3, 4, 10 stages, we will find the solar sequence number adding up to 60 B-poles as predicted from part 1. But we have a problem that here they are not in the correct sequence, 3, 1 instead of 1, 3, 4. Also, we need an additional rotation at the pole before the cycle starts to adjust this rule of thumb. So we have two problems, and we'll see now if they can be circumvented by replacing the integral numbers of the solar sequence with decimal numbers. The decimal numbers of generalized Fibonacci numbers were called proxies in part 1. We start from a large member of the solar sequence and divide by the mean and extreme ratio. We arrive at the sequence of numbers with the decimal parts, and you see we can adjust to the numbers, to the sunspot groups number 1 to 10. Now these decimal numbers, 22.9 to 0.301. So when we use these numbers in replacing in the preceding table, this is the numbers, and we do not have the discrepancy of having 3 before 1. It is in the correct increasing sequence. Also, here we have figures smaller than 1. We do not need a full rotation at the pole to adjust artificially, arbitrarily, this rule of thumb. Now, if we compare with the characteristic values found from observations for the numbers of B-poles for sunspot groups, we have a better fit compared to a factor 1.5 or compared to the integral numbers of the solar sequence, but still we have several problems. Here we have more than 14 instead of 12. And for these three groups, we have large discrepancies. The main advantage compared to factor 1.5 is that we suppress the excess. We have almost exactly 60 B-poles using this rule of thumb. So the interest of this approach with the solar sequence numbers is that we would be able, if the fit was convincing, to reply to the two questions, what is the distribution and why is it so? Because we would get the sequence of the numbers of B-poles from the sequence of differential rotations over the entire Schwabe cycle. However, we will maybe find a still better fit from another simple rule of thumbs using certain divisors of the number 120. Those which are also divisors of 144 approach our observed sequence very well, which is also interesting from a point of view of finding some hint at a causality. Is actually the number of rigid rotations of the solar cycle. This definition corresponds to retaining only the divisors of 120 which are not multiples of 5. As you can see in this table, these are all of the divisors of 120, and these are those that are not multiples of 5. You see, we find numbers which are close to our numbers of B-poles, 24, 12, 8. The problem is that we have only 8, but we have 10 sunspot groups. So if we now compare all of these possible fits, we find that the best fit by far is obtained with the divisors of 120, which are also divisors of 144. You see the variance which is shown here is half the variance with the solar sequence numbers. But unfortunately we have only 8 groups. So the two smallest groups are missing if we predict the distribution of the numbers of sunspots and B-poles per sunspot group from the divisors of 120. This is as far as we can go in this investigation. This is now, ladies and gentlemen, the end of video 29. In the next video, we will concentrate on the truly spatial distribution of sunspots. I thank you for your attention.